going to talk about speed of gas particles. Maybe. There we go. Basically, how fast do particles move? Okay, the kinetic energy of any gas, let's start there. It is equal to 3/2 or 3 RT over 2. Okay. So what does that mean? That's for any gas. And at least any ideal gas. Do you see anything in that equation? Kinetic energy is equal to 3 RT over 2. Anything about the identity of the gas, the number of moles, anything like that? No. The kinetic energy is independent on the type of gas we're dealing with. It's only dependent on the temperature. That's the only variable, temperature. Maybe I should just write that. That's Kelvin temp. And since we're at it, why don't we write what R is? This is at 8.314 joules per Kelvin per mole. That's R. Okay, so we're only, and this will give us units of joules per mole. So that's the kinetic energy of 1 mole of a gas. Doesn't matter what the gas is, it only matters what the temperature is. So if we have 2 gases, one's hotter, it will have more kinetic energy. That makes sense since we know that kinetic energy is proportional to the Kelvin temperature. All right, now let's talk about something we call root mean square speed. Okay, and that's abbreviated U sub RMS. The U is the speed, RMS is the root mean square. What the heck does that mean, root mean square? Just think of this as the average velocity. There's more to it than just average velocity, but when you see that U sub RMS, just think average velocity of a gas sample. So let me give you the equation. U sub RMS is equal to the square root, and this is where the root part comes from. Let me fix that. The square root of 3 RT over capital M. Okay. R is the same as it was in the equation before, 3.14 joules per Kelvin times moles. T is the Kelvin temp. And M, this is molar mass, kind of. The units for this molar mass have to be in kilograms per mole. And that has to do with the unit of joules in R. I'm not going to go through the math on that, but just know that molar mass here has to be in kilograms per mole. And I'll give you a real quick and easy way to get kilograms per mole. So if we have CO2, for instance, and CO2 has a molar mass of 44 grams per mole, that is just equal to 44 times 10 to the -3 kilograms per mole. So just take the molar mass, multiply by 10 to the -3, and that puts it into kilograms. That's not proper scientific notation, so you wouldn't want to give your answer that way, but that's good enough for our purposes here to plug it into the equation. And you can type that in your calculator, no problem. So what does that mean? What does this equation mean? Well, basically, like I said, it gives us the average velocity of gas molecules. So let's see how fast a gas molecule is moving at roughly room temperature. Okay, so let's just look at 3 different gases. So we'll have the gas, and this is at 25 degrees Celsius, and then it's URMS, root mean square speed. So helium at 25 degrees Celsius, helium is obviously very small. Okay, so that gives us a small number here for M. So do you think we're going to have a big root mean square speed or a small one? If you said big, you're right. Okay, divided by a smaller number, that gives us a bigger answer. And that is about 1360 meters per second. Which, if we double that, that'll give us a pretty good idea of miles per hour. So, what, 2,600 miles per hour or something like that. Think about that, 2,600 miles per hour. That is really, really fast. Okay. Water, H2O. Its root mean square speed is 650 meters per second. Again, about 1,300 meters per second, incredibly fast. And then CO2, 415 meters per second. And I guess I can put this is about 2 grams per mole. This is 18 grams per mole. And this is 44 grams per mole. Okay, the bigger the mass, the slower the molecules are going. Why is that? It's because kinetic energy at a given temperature is fixed. Okay? So in order for kinetic energy to stay the same, the bigger molecules have to go slower. The smaller molecules have to go faster. That's how kinetic energy stays the same. So what that means is if I open, like say, if we're in the classroom and I open a jar of something with a molar mass of 44 grams per mole, and it was really fragrant, like say vanilla or something like that, boom, it should be up in the back of the room instantly. But that is not the case. The reason is what we call mean free path. Mean just means average, okay? So the average free path a molecule takes. So let's just say we have a little molecule here, and it wants to get to the other side of the screen. Let's just give it a target. It's going to try and hit that target over there. Well, what it's going to do is going to go this way, and then it's going to run into another molecule, and it's going to go this way, and it's going to go this way, and it's going to go this way, and it's going to go this way. And it's going to have to keep doing this little dance to get across. This is kind of fun. To get to our target. So you can see it has to travel a lot further. And why is that? It just runs into other molecules. Okay. All along the way here, there's a molecule here and here and here and here. And everywhere it just keeps bumping into other molecules and it can't get anywhere. And that's what we refer to as the mean free path. And that's what seems to slow what we call diffusion down. We'll talk about diffusion in a different video. Okay. So let's just look at distributions of velocities real quick. So I'm going to draw two simple graphs. They're going to be very similar. Okay, this one we're going to plot. They're actually going to both be the same plot, number of molecules, and down here we're going to have velocity of particles, or molecules, I guess I could say. Or more technically, we should make this number of particles. Sorry. Okay, so what happens is if we look at three different gases, and we're going to look at three different temperatures of gases. One, rather cool. Wow, just assume that's, nice and smooth. Okay, kind of a cool one, a warm one, and when I say cool and warm, of course, those are all just relative. Okay, so this is the hottest. This would be the coolest. And the green one would, whoa, hello. Go away. The green one would be the middleist. That's a word I made up. Okay. Coolest, hottest, middlest. And you notice the graph on each one, as we go from the coolest to the next to the hottest, the graph spreads out. This part goes that way, and the top goes down. You see that happening? And that's because they're always anchored over here where the velocity of the particles is very, very slow. But the average, which the center is the average, okay? The average velocity increases. All right? And in order for that to happen, same number of particles, it just has to spread out. Okay, it's a very similar looking graph, but this time we're going to plot different gases. Whoa. With different, sorry, not with different anything. The same thing, number of particles. And this will be the velocity of the particles. Okay, if we have a really slow moving molecule and then a faster molecule, and this graph does exactly the same thing as the last one. Okay, so in terms of mass of the particles, which would you say is the heaviest, the yellow or the green? Well, this is the lightest, because the smaller the particle, the faster its the smaller the gas, the faster its particles are going. There's the average on all of them. Okay, just right there in the middle. And you can think of these distributions kind of like grades. When I say you guys have got an average of 66 on the exam, we all know that some people are below that, some people are above it. And it's just an average because it sits right in the middle. So that's the heaviest molecules or particles. And purple is a little bit lighter, blue is a little bit lighter still, and green is the lightest. That's it for now.